start recording. So one thing that I want to mention is specifically about problem number 2, okay? Because I saw some trouble with free body diagrams, okay? So when you see something like this, first of all, what is this that we analyze? What type of a structure system is it that we're dealing with here?
A machine.
It's a machine, right? So how do we analyze a machine?
We have to break it apart.
So we take it apart. We take each member, right? And you draw a free body diagram of each member. Okay. But let me ask you a more general question. We're almost done with the statics, the whole thing, right? If you're talking about free body diagram, so what is the purpose of free body diagram? Why do we even bother with free body diagram? Because the problem has a figure, right? So they gave us this figure. Why do we have to go ahead and draw another diagram called free body diagram? Why can't we just use this figure that's given? Anybody? Someone said not enough space. What if I give you a huge sheet of paper with lots of space? What is the purpose of free body diagram?
You have to have the reactive forces out of the pins and the normals.
Okay. Why? Why do we have to do that? Why can't I just look at this figure, the one that in the border, and just start writing equations? Because a lot of you guys did. You guys are like, I don't need a free body diagram. I just have a figure. I'm going to go off based off a figure. Why can't you do that?
You have to isolate the two parts so that you can put them in equilibrium.
Yeah, you're telling me how, how I should be solving it. I'm asking about why. Why do I have to do that? Why do I have to isolate them, do all those stuff?
If you add them all together, you'd have too many equations. You're trying to simplify it with each, trying to basically get each forces so you can find each force by himself.
Okay, and why can I not just do that using this figure right here?
Once you have too many equations, then unknowns.
Too many equations, unknowns. Okay, what else? I mean, this is a pretty important question, don't you think so? You're doing all this statics course and you're learning about free body diagrams. Shouldn't you know why do we have to use free body diagrams?
Don't you have to create two? Because if you tried solving it with the whole thing, everything will cancel out. Like your two p's would cancel out if you use the top figure. So there'd be no way to really solve for p then. Like, because if you tried using momentum on like A, the two p's would like cancel out automatically. Same with the two normal forces on B. So you can't really solve for anything there.
Okay. So yes, everything that you guys told me is correct. Okay. Everything, none of it was incorrect. Yes, they're all correct answers. But the more general question is, it says find the clamping force on a smooth pipe B, right? Do you see a clamping force on this diagram? Do you see any clamping force on point B? And this figure right here.
No.
Okay. Do you see any force on A?
On that figure, no.
No. So the reason we create free body diagram, we take these apart, all of these trusses, anything, any problem that we do, is to reveal the forces that we are looking for. Okay. So the reason behind FBD is let me get this, is to show or reveal all known and unknown forces, okay, that are exerting on that body, exist or exerting on the body. Without drawing the free body diagram, you are not going to see all the existing, all the known and unknown forces that are exerting on that body. All right. So that's one thing, which I see not a lot of people, what's very few people missed. All right. And I've kind of seen that repeating in every exam. They don't see a need for free body diagram. They just redraw the figure. Okay. We're going to see some free body diagrams that you are going to see. Someone is trying to redraw this and put this. Okay. Why? If I give you the figure, why do you see the need to redraw it? Okay. If it's not adding any value to your solution, it's not providing any additional information to you guys. Okay. That's one important thing. The second important thing is there are a lot of people, well, again, few people that draw the free body diagram, okay, but without putting forces on there. They draw pipe B here, A here, and they don't put forces. But when you look at their equation, they have forces in the equation. All right. And when I grade those exams, I always look back and says, you have NB here. Where is this NB? Okay. Is it, if you can use your imagination and memory, why do you even bother with this if you don't want to put all the forces on there? So free body diagram is something that you have to use to solve your problem. It's not just some luxury that we ask you guys to do it or require you draw it just so you have drawn it on there. You have to use it. If you don't see a force on the free body diagram, then you shouldn't be putting it on there. If you have extra forces, you cannot ignore some of the forces on your free body diagram, okay? So now let's look at some of the answer that were submitted, and we can you can see. So here's one that was submitted for, or a couple of them that were submitted for trusses. Okay. So what are the two ways that we analyze a truss?
By joints or sections.
Okay, so we use method of joints, right? The method of joints, which we draw free body diagram of a joint, right? One pin. You draw free body diagram for a pin. Or method of sections, which you cut your truss in half, draw free body diagram of half of your truss. This is the only two way that you analyze a truss, okay? So when I see free body diagram, and these are not the only one, there were quite, few similar to these ones. So what I have a free body diagram of this? What is this? Is this a section? Is this a joint? Is this bunch of joints together? Is it bunch of sections together? What is it? Can anybody tell what this is? So again, we go back to, you got to think about, we are not just drawing a bunch of forces to satisfy and check a box and move on. You draw free body diagram in order to use it. Okay, it's like a map. All right. So when I see a free body diagram like this, I don't even know how to use this because I don't even know what this is. Remember, method of joints is analysis of a particle. Method of section is analysis of a rigid body. These are not just beautiful names that we tell you. You have to understand the meaning of a rigid body. You have to understand the meaning of a particle. When you look at this figure, you can't tell what it is. So it tells me that you only don't understand free body diagram, but you don't understand particle, you don't understand rigid body, and you don't understand trusses. So there goes 4 chapters of statics. Okay. Or another problem like this. What is the first step of free body diagram? Step 1 in free body diagram.
Reactive forces.
Step 1, before that.
Isolate.
Like the particle.
Isolate, right? And draw outline. So whether you're drawing outline for a pin or your half of your truss, the first problem I see here is like, this is not isolated. Again, someone redraw trusses, okay? But then I shouldn't say I don't understand because I understand what they're trying to do, but what is this? It's not a pin. You're not drawing free body diagram of a pin. You're not drawing free body diagram of half of your truss. So there's so many issues here that you have to consider. You have to think about, right? So now let's look at some of the free body diagrams that were submitted for that clamp problem. Okay, so here are 2 examples of redrawing the figure that's already given. Okay, again, you have to think about it. What is it that I'm trying to get out of drawing this? Okay, by redrawing the figure, how is that going to help you with solving? You already have the figure in front of you, a more beautiful, elegant figure. So why do you see the need to redraw it? So this is not a free body diagram. Redrawing the figure doesn't mean free body diagram, okay? Here's another issue. What is the problem with this one?
Not isolated.
It's not, the members are not, so again, you got to draw in the machines and frames, you draw a free body diagram of each member, right? So this is not separated, so it's missing a whole bunch of forces. So why not put a force here? And as someone said when I was asking, look, so let's write summation of forces in Fy equals 0, right? I have an AY, I have an 80 newtons going down, I have an 80 newton going up, I have an A, I'm assuming AY, okay? And these 2 cancel each other out, so equals 0. So it's not in equilibrium there based on what you draw for me, right? Summation of forces in X equals 0. These 2 again cancel each other out. You have an AX there. So either it's not in equilibrium or they don't exist any force. You see how many problems we run into when it's not free body diagram of each member. Okay. There were some other with like issues. Again, this one, someone just tried to put one force here. So if you want to do that, you're missing a whole bunch of other forces all over the place, right? So again, not isolated, not a free body diagram. Here's another one that I saw. If this is a machine or a frame, we draw free body diagram of each member. You cannot draw free body diagram of a pin, okay? Because let's see what happens. Let's see if you want to use this, right? So let's write equations of equilibrium for this one. Summation of forces in Y equals 0. AY equals 0, okay. Summation of forces in X equals 0. AX equals 0. Okay, so both of these are 0. All right, let's do this one. So pretty much by drawing a free body diagram like this, you conclude that all forces on everywhere on this is equal to 0. So pretty much any force doesn't exist on this, okay? Let's look at more. Let's see. Okay. Same problem as we discussed before. I see a attempt at a free body diagram, right? So they did a step 1. They isolate, took each member. But then, so where are the forces? Again, you got to think, what is the purpose of a free body diagram? Shouldn't the forces be showing? Okay, but then there's a CB, so I'm assuming there's a force CB here. Okay, where are the forces on A? So not a free body diagram again. This is not called a free body diagram. Here's another issue that some people run into. Same as before, pin A, pin B. Okay, and this person, I think, tried to solve these two together. Okay, so if they're together, they need to be on a member. If they're not together, then this is one free body diagram. It has its own equations. Okay, X and Y, and this is another one. So again, you cannot combine two different free body diagrams and write one equations for them. This is like wrong on so many levels. Plus, what happened to the existing force of 80 newtons or 80 pounds that was on there? So you can't ignore part of your rigid body and start doing that. So important message is, again, this is not to embarrass you guys or you know, make fun of the solutions and stuff. You're trying to learn from it, okay? Important thing to learn is you have to follow the 3-step of a free body diagram. Absolutely. Step 1 is isolate and draw outline of whatever you're trying to do. Okay. Step 2 is to put existing or active forces on there, right? If you're drawing a free body diagram and I give you a force of 80 newtons, you cannot ignore it. Step 3 is reactive forces. The forces from pins, supports, and all of that, all right? Again, you cannot draw a free body diagram. Let's see if we can go back. Well, can't go back. You can't draw a free body diagram and there we go. And not draw. So they did a step 1 and 2, but they didn't a step 3, which was reactive forces. See that? In these ones, they didn't do a step 1. Step 1 is not done. Step 1 is not done. Step 1 kind of done. Step 1 is missing. Step 1 is missing. Step 1 is missing. See, if you follow those 3 steps, you are able to draw free body diagram for every problem that you're going to face in statics and dynamics and mechanics of material, all of these courses. Okay, so remember 3 steps of free body diagram. We're going to talk about it a lot today. So please check your solutions on Blackboard, my grading, and all of that, and let me know if you had any questions or any trouble. There were some people locked out of the test, and they emailed me. They all reached out to me. I got back to every single one of you guys. I checked your work. I adjusted your grade. So if that's all taken care of. If you emailed me or you were locked out of the system and you emailed me and you did not get a response from me, make sure to email me. There shouldn't be any. I went through the list twice. But if I missed someone here and there, please let me know and we'll work with you and we'll make it fair for your exam. So sorry that happened. I've used this publisher 11th semester. This is the 11th time that we're using it and has never crashed or anything. So it was kind of first time that happened. I think there were about 15 people out of 100 that they were affected by it. Okay. So let's start with a new chapter. Okay. So we're going to start chapter 8 and dry friction. Why am I missing chapter 7? Why am I skipping chapter 7? Anybody? Any guess? What is chapter 7? Let's see how many people have done next activity.
Internal loading.
So chapter 7 is about internal loading, all right? Yes. So we did just a little bit of internal loading when we cut the trusses in half, right? So whenever you make a cut, you are going to reveal the internal loading, all right? Trusses are two force members, so the forces are along the axis of the truss. So whenever you cut, the forces are going to be in the direction of the axis of that member that you cut. Chapter 7, which has only one section to read, section 1.7.1. And that's what I put it as a self-read and self-learning. So you're just going to read it on your own as part of activity 7. Is a little bit more general. It's cutting through pretty much any member, and you're going to reveal the internal loading that could be an axial load, a normal load, a shear load, and a moment. So that's something that you guys need to do on your own. Again, it's only 7.1, but that gets covered quite in depth in mechanics of materials. Okay, so that's why we used to mention it in 1 or 2 lectures in the statics, but now it's a self-read, and you guys can just read that 1 page of the textbook. Okay, so next section that we're going to talk about is dry friction. Okay, so let me just make some okay, should have done that first. All right, so let's think about it. What is friction? What is friction? I'm sure all of you know what friction is, but can someone give me a statics or engineering definition of it? Okay, Merrick, I'll answer that question at the end. Okay, what is friction?
A resistance to movement.
Okay,
Is what
a resistance to movement. Again, think about in a statics term. We are in a statics. What do we learn in a statics? What are we dealing with in a statics? What were we just discussing a couple of minutes ago? What are you guys trying to find? What are you guys trying to
A
calculate?
reactive force.
Forces. Okay, more general. So force. So friction is a force. All right. So that means immediately when you think of a force, you think of a vector. And when you think of a vector, what does that mean?
It's a force in a direction.
So it has a magnitude and it has a direction. All right, so just remember. Now we're going to talk about the magnitude and we are going to talk about the direction of it. But you're right, it's a force that resisting movement of two contacting surfaces relative to each other, or they're sliding relative to each other, okay? It is always tangent okay, not parallel, those are different, is tangent to the surface, and it is opposite direction of movement. Okay. The magnitude of it, it is proportional but by a normal force. This means proportional. Okay. Normal force is the force that is pushing those two surfaces together. All right. Any questions so far? So it's a force. It has a magnitude, which is, this is the magnitude of it. And the direction of it is tangent and opposite direction of the movement. Okay. Is it clear so far? Okay. There is one very important graph diagram that I want you to remember. Okay. We have force P, which we're going to explain what it is, and there is friction force. Okay. I have a box sitting on a surface. It has a weight of W. Okay. It's just sitting there. So what is the friction? What is the friction force on this one?
Wouldn't it be 0 because it's not moving?
It's not moving, okay? Remember, friction is a force resisting a movement. If there is no movement, it's not going to resist. All right. So at this point, it's 0. Then I'm going to apply a little small tiny force here called force P. What happens then?
There's an opposing force of friction.
Okay, there's going to be an opposing force of friction. Does this box start moving or no?
Yes, it would start moving if you have a force applied to that way.
It has to overcome the coefficient
Depends on-
of static friction.
Okay, so the answer is it might move, it might not move. You don't know. All right. If you start pushing on your desk, it might not move if you're just pushing very lightly on it, right? But if you start pushing really hard, it might start moving. So the answer is I don't know. But I told you a very small force. So this is 0.0. This is my force P1. If I apply a small force P1, it is going to generate friction force F1, which is tangent to the surface. I can't quite show it tangent, so I'm going to show it with a little distance. What is tangent? Means it's on the surface. I'm going to increase my force a little bit more to P2. Okay, that's going to create a bigger friction force for me of F2. Okay, and then I'm going to reach a point where that's the largest force that I can apply before this block starts moving. Okay, this is like bold force P. So up to this point, no movement. Everything is standing still. But right now I'm at a point that if I start applying just a little bit more, this block will start moving. This point is where we take as statics friction, that S referring to static. And remember I said the magnitude is proportional to the normal force. In this case, that proportion becomes an equal with the mu s, which is coefficient of static friction. Okay. So it is only, this is very important, only and only at this point, which we call it impending motion. At the impending motion point. Okay, this equation is only and only valid at impending motion point. So this graph kind of looks like this. It's a straight line going up. What do you think happens after this if I keep increasing the P to a huge, large amount?
The P overcomes the friction and the friction becomes like more constant.
Okay, so a couple of things happen. The first is the box or the blocks start moving. All right. The other thing is, as someone said, the P overcomes frictions, it starts moving, and the friction stays constant. But that one is called kinetic friction. So the graph drops a little bit, and then it stays constant like this. Okay. So this point, there is movement. All right. This one is called Fk, and that's kinetic friction. That one is also, we refer to as mu k n. Okay. This one is coefficient of kinetic friction. All right. So now here's a question. Why is Fk is smaller than Fs?
Because the first Newton's first law, like an object that's in motion tends to stay in motion, so it's you have to get past like the breaking point of the friction.
Okay, that's actually a very good explanation. Okay, but that's more of an equilibrium. Okay, and yeah, I would say you're right. That's correct, but that's not quite the reason why Fk is smaller than Fs. Okay, and I'm not expecting you guys to know this, but this is more of a just see how you think. So here it goes back to change in mechanism of friction. Okay, so when this box is sitting, it's important to understand why there's friction. When this box is sitting on the ground, if I zoom in, the box is something like this. And the floor or the ground or the other surface is kind of like this.
Dr.
Okay.
Amir,
Yes.
Kira wants you to go back to the previous slide for a second, I guess.
Oh, here. Okay. Is that good?
Yep.
All right. So there are ridges and grooves and stuff like that. So this one is trying to go this way, friction is this way. So these get entangled with each other. Okay, so in a static friction, when we are in this section, we said there is no movement. Okay, the mechanism of friction is more entanglement. Okay, when the movements start happening, these ridges start sliding on each other. Okay, so the mechanism becomes a sliding, those ridges and grooves and stuff. So that's why it's a little bit easier and it requires a little bit less force to overcome that movement and stuff like that. So just remember, kinetic friction is a little bit smaller than static friction. So which of the coefficients do you think is smaller, ms or mk?
Well, considering its multiplication and and MK is smaller than, I mean, FK is smaller than MK would be smaller.
So ms, I should have put them the other way. Ks, you're correct. So because n is constant, the normal force is constant, and so the coefficient of kinetic friction is usually less too. It's usually, I think, 25%. I had it somewhere. Yeah, typically 25% smaller. All right. What is the unit of coefficient of friction?
Would it be nothing?
It doesn't have any unit because this is newtons, this is newtons, or this is pounds, right? These are forces. So therefore, mk has no units. It's a coefficient. It's usually a number. Some of the typical numbers between 0.3, 0.5, this is for metal on ice. 0.3 to 0.7, this is like wood on wood, two wooden surfaces. 0.74 to 1.2, it's copper on copper, you know. So these are just some typical numbers for mu-s. And mu-k is usually 20, 25% less than that, all right? Okay, I think we're ready to do a problem, all right? So let me see which one we can do. Okay, you know what, let's do a simple one. I don't know if we can finish it, but we can get the free body diagram done. So same as any other problem that we've done that requires equilibrium, this step one is free body diagram. The only difference is now you have an additional equation that helps you solve, and that one is this equation in addition to your summation of forces and summation of moment equals 0. Okay, so it's just an additional equation, but don't forget this is only valid at impending motion. So not always we have impending motion at all of the surfaces that are contacting, all right? So let's see. So let's draw the free body diagram now that has friction force in it too. So determine the smallest coefficient of static friction at both A and B needed to hold the uniform 100-pound bar in equilibrium. Neglect the thickness of the bar. Mu A, mu B, same, just mu. Okay. All right. So it wants to figure out what is the smallest. It can be bigger, all right, but there's a little smallest amount of coefficient of friction that should be there in order to hold this bar where it is. If it's less than that, it starts sliding down, right? If it's more than that, doesn't matter, it's gonna stay. So we need that smallest. Step one, I told you, is to draw a free body diagram of bar AB, okay? Step one, we just talked about it. What is a step one? Step one of free body diagram.
Isolate.
Isolate and outline, right? So all I have to do is do that. Step one is done. Step two, what is the step two?
Forces.
Sorry, what was that?
Active forces. From
Active forces, okay. For this problem, what is my active force?
The weight.
the weight, right? That's the only thing I have right here, which I put it in the center. It says 100-pound pointing down. All right. Okay. Step 3. What is the step 3?
Reactive forces.
Reactive forces, the forces that are holding this in place. There are 2 points that I see, A and B. So now this problem has friction, so you have to add another reactive force from now on. So another reactive force, which is force of friction. We usually just put F, show it with F. And it's always opposite of the direction that this bar will move, okay? So let's just start with point A. Before knowing anything about friction from chapter 5, if this was a rigid body, what kind of reaction did you have at point A? Don't think about friction yet. If this was a chapter 5 problem, what kind of reaction did you have at point A?
Be like a roller, right?
Yeah, it's pretty much like a roller. Or we know it as a smooth contact, right? So what is a reaction at a smooth contact?
A normal force.
Just a normal force, right? Perpendicular to the surface. What about point B? Again, if you didn't know anything about the friction, what would be the reaction at point B?
Wouldn't it be the same?
Okay, so the point B also has a normal force, which is perpendicular to that surface or point of contact, all right? So this is the bar. This is that point B. It's going to be perpendicular to this, to that edge. A is like this, and there's the surface. It's going to be perpendicular to that edge or that surface, okay? Anybody following so far? So far, this is just a free body diagram based on what you knew in chapter 5. If this problem said this surface is frictionless or friction-free, then this was your free body diagram. But we know there's friction, okay? So friction force remember, it was tangent, opposite of direction, opposite of movement. We're not going to have movement, or maybe we do, we don't know. But we're thinking about possibility of the movement. If this bar wanted to move, which way it would go?
Left.
Okay, it would go to the left, right? It would kind of drop and go to the left. So point A would go to the left, point B will kind of slide down. So this is the movement. These are not forces. Okay. So now let's see. At point A, I have to put a force that's tangent. If this is normal, tangent would be this way. And it's opposite of the movement, so I'm going to put the arrow going this way. And I'm going to call this FA. At point B, it's going to be tangent. If this is my normal, then the tangent is this way. And then I'm going to look and see the arrow is coming kind of down. So the friction is going to be opposite and going up. Okay?
Friction almost always be perpendicular to your normal force.
It is. Yes. That's another. Because your normal force is normal to your surface. And friction is always tangent to the surface. Yes. You know. So this is your free body diagram. Okay. Now what? How many unknowns do you have here in this free body diagram?
4.
4. I have FA, I have FB, I have NA, and I have NB. How many equations do I have?
Or 3.
Okay, someone said 4, someone said 3. So it can be less than 3 for sure. Because we have this, right? We have these 3. It's a rigid, kind of like a rigid body. So we have these 3. What are the additional equations that I have?
The new friction equation.
Okay, so the friction equation is going to be at, but it's only at impending motion, all right? And I'm going to tell you what it means. I'm going to kind of finish this problem on Friday. Okay, but I'm just going to briefly mention it. So if you guys want to do it on your own. And so summation of moment about point A, that's one of my equations that I'm going to write. It's going to be NB 13 feet minus 100. This is going to be, it's going to be 5, 12, 13, the slope triangle. So it's going to be 112 over 13, 8 feet equals 0. That's one equation. I write summation of forces in x equals 0. Anything that goes this way is going to be positive. So it's going to be FA minus NB. This time it's going to be 5 over 13. FB, and it's going to be 12 over 13. Okay. And the last equation I have for now, at least, is going to be NA minus 100, NB 12 over 13, FB 5 over 13 equals 0. Okay. I can find NB right away. From this first equation, it gives NB of 56.8 pounds. Okay, so 56.8, 56.8. After this stage, that's what and you have to write this. I assume that's slipping, I'm done in like 10 seconds. Slipping happens at A and B at the same time. Okay, because it's the same bar. Not point A can start slipping without B slipping or vice versa. After doing that, then you can write this equation. Without writing this sentence, this equation would be invalid. Okay. And then I'm going to pick up from here on Friday. I have added a lecture on friction to the list of lectures and videos. Please watch that for Friday. I explain the graph better, the equation better. It's a lot more detail on friction. So please watch that for Friday. But I'll continue this problem on Friday, and we're going to do friction Friday. Okay. If you have any questions, I'd be happy to answer. Otherwise, you guys are good to go.
Yeah, I missed how you got the 56.8 at the end there.
So this one was from this equation right here. There's just one unknown, and that's NB. Everything else is just numbers, you know.
Oh, okay, okay.
Yeah,
Thank you.
just one unknown. Yes.
All right.
Okay, so okay, Merrick, or did someone have another question? Okay, let me see. Oh, okay. Josiah, are you still online?
Yep.
Yes. Okay. So here's let me stop the recording.